Hello everyone and thanks for watching Edupedia World videos. I am Manish Agrawal and today in our topic of mole concept we'll start with Avogadro's law. In the last session we studied empirical formula, and once we have a more basic understanding of mole concept and chemical reactions and how we conserve mass in them, we'll further again take up the topic of empirical formula and related questions. Alright, for now let's study Avogadro's law. Okay. So before we start, let me remind you that it is one of the most important law you will come across. Okay, you have to constantly use it, not only your class 11th but also in class 12th and even in your further studies later on. Alright, and even in physics you might have to use it. Okay, so remember this law and get a grasp of its applications. Okay, so let's begin. Now Avogadro's law, it states that at same temperature and pressure, equal number of gaseous molecules occupy equal volume. Alright, let's give it a second and see what exactly this means. See, at same temperature and pressure, so I have fixed the container's temperature and pressure. Okay, once I have done that, what I am saying is, or what Avogadro said was that equal number of gaseous molecules will always occupy equal volume. So basically he didn't say anything about the type of gas. Alright, he didn't say anything about any other condition, about the location of gas, okay, or say altitude of the gas, okay, or any other concept or any other formula which is needed over here. Okay, he just said that if you have say 10 molecules of gas 1 and if you have 10 molecules of gas 2 at same temperature and pressure, then both of these gases will occupy same volume irrespective of the type of gas. Okay, and whether you measure that volume here in India or in Pakistan or in US or in Canada, it will always measure same. At a given temperature and pressure, the volume will come out to be same. Okay, in other words, whether my gas is nitrogen, alright, whether my gas is nitrogen or carbon dioxide, okay, or say some other gas, methane, okay, all of these gases, okay, and any other gas will occupy same volume for same number of molecules. When I say number of molecules, how do we measure number of molecules in physical chemistry, okay, or in chemistry? We use moles. Alright, instead of counting single molecules, we usually count moles of molecules, because we have a bunch of molecules together, okay, and that bunch is usually very large, so we prefer measurements in terms of moles. So equal moles of gaseous molecules will always occupy equal volume. You can also see it other way around. Alright, that is equal volume will have equal moles of gas. So if I tell you that I have one container, say one container of steel made up of steel which contains 1.5 liter of nitrogen gas, okay, then I say I have another container, say of wood. I have a wooden container, okay, and in that wooden container I found out that my methane's volume is 1.5 liter again. Okay, so what I can say about these two gases, I can say that if I have done the measurement at same temperature and pressure, for example, if temperature here was T1 and pressure was P1, similarly the temperature here was also T1 and P1, so I have done both the measurements at same temperature and pressure. So this data 1.5 liter and 1.5 liter can be used to say that the moles of molecules of N2, okay, the moles of molecules of N2 and that of CH4 are same. Okay, the moles of molecules of N2 and that of CH4 are same because they have both occupied same volume at a given temperature and pressure. Okay, so let's say again I have CO2 coming from the exhaust of my car, and that CO2 measures 1.5 liter but at a different temperature and pressure, say T2 and P2. Okay, this time temperature and pressure are different. So if I have changed the temperature and pressure, it means that the number of moles of molecules of CO2, okay, the number of molecules of CO2 or moles of CO2 are definitely, okay, not maybe, but definitely going to be different from this. Okay, let's say this was N1, so they are definitely going to be different from N1. So I might have more or less number of CO2 molecules, but they will not be same as that of N2 or CH4. Okay, this is what we understand by Avogadro's law. Let's go into further detail. Let's note some points here. Okay, let's see some of the notable points. Okay, first notable point, I am only talking about gaseous molecules. Avogadro gave this law only for gaseous molecules. This law is not applicable if the substance you are measuring is in liquid or solid state or any other state. Okay, it is only applicable for gaseous molecules. Similarly, molecules and not atoms. Okay, now this is a very important point. Avogadro said that equal number of molecules occupy equal volume. He didn't say equal number of atoms. Okay, so in the previous case, we won't count number of atoms of nitrogen. We will count number of molecules of nitrogen, that is N2. We will count N2 as one molecule. We won't count two atoms of N. Okay, you will always have to note that you will count molecules, not atoms. Similarly, if you have oxygen, you will count O2, not O. Or if you have ozone, O3. Okay, so he said molecules, not atoms. Alright, let's go into further detail of this point. See, when Avogadro gave this law, we didn't actually have a clear understanding of atoms and molecules. In fact, when he gave this law, people didn't accept it because at that time Dalton and other scientists believed that atoms are what exist. Okay, they didn't differentiate between atoms and molecules. They didn't know that molecules are basically nothing but made up of different atoms. Okay, they didn't believe that molecules can be polyatomic. Alright, so this was the first time that we had an indication about difference between molecules and atoms and about existence of substances in forms of molecule. Avogadro kind of observed this and may have realized that substances basically exist in form of molecules and not atoms. Alright, so that is why we used molecules here, N2, O2, O3, not N, not O. Okay, not Cl, we use Cl2. Okay, but let's say we have a gas, say helium, okay, or say argon. Okay, let's say we have a gas like helium or neon or argon which exists in atomic form. Okay, you do not have He2. Okay, you do not have He2. We have He. Alright, we have He. Similarly, argon, krypton, neon, they all exist in atomic form. So these gases, okay, these gases which exist in atomic form will follow Avogadro law based on their number of atoms. Alright, so it is dependent on molecules or atoms. Okay, now we since have a better understanding of molecules and atoms, we can directly say that number of gaseous molecules is equivalent to number of volume. Okay, sorry, same gaseous molecules will occupy same volume, or same gaseous atoms will occupy same volume. Depends on existence of gas, whether that gas under standard conditions, under the ambient conditions at which you are doing measurements, exists in form of molecules or whether it exists in form of atoms. Alright, so these gases are basically can be said to be atomic gases because they exist in form of atoms, and whereas these four gases and most of the gases which you will come across can be said to be molecular gases because they exist in form of molecules. Alright, okay, in case of atomic gases I can say moles of atoms. Okay, gases with same moles of atoms in different containers or in same container will occupy same volume. Okay, so this is what we mean by Avogadro's law. Let's see next point. Volume won't depend on atomicity or mass. Alright, volume won't depend on atomicity or mass. Okay, see here, atomicity is what? Okay, you have to remember this term. Atomicity means number of atoms in a molecule. For example, in N2 I have 2 atoms in one molecule, so atomicity of N2 is 2. Alright, similarly Okay, in O3 I have 3 atoms in one molecule, so atomicity of O3 is 3. In CH4 I have 5 atoms, 1 plus 4, 5 atoms in one molecule, so atomicity of CH4 is 5. Okay, and obviously masses of each of these gas. Okay, let's talk about molecular mass. So molar mass of each of these gas is different. N2 has molar mass of 28 gram, ozone has molar mass of 48 grams. Okay, CH4 has molar mass of 16 gram. So molar mass of each of these gas is different. Basically these gases are completely different. They have different properties, they have different atomicities, they have different molar masses, but it doesn't matter as long as you have same number of molecules. Say I have 3 molecules of N2, 3 molecules of ozone and 3 molecules of methane, then they will all occupy same volume, okay, at a given temperature and pressure. Occupy same volume. Volume means the space occupied by a substance. Okay, space in 3-dimensional. Okay, we understand 3-dimensional right now, not more than that. So space occupied in 3-dimensional, okay, is the volume of a substance. Alright, let's see the next point. So there are several examples for this. Okay, you'll further on we'll see several calculations even in our gaseous states of matter topic. We'll do many examples based on this. Okay, so for now let's move on further and see some notable temperature and pressure, some standard temperature and pressure for which we have to study these things. Okay, so let's say I have ideal gas. Okay, what we mean by ideal gas, we won't study it over here. For now, let's assume that all the gases we are dealing with are ideal gas. You do not have to think about what ideal gas means. Alright, we'll take it later on in states of matter in great detail. Okay, in fact that whole topic is based on nothing but ideal and real gases. Okay, so assuming ideal gas, okay, let's say I have STP condition. Now what do we mean by STP? STP means standard temperature and pressure. Okay, that is temperature is equal to 273 Kelvin. 273 Kelvin is 0 degree centigrade. Alright, 273.15 actually. So 273.15 we approximate it as 273 Kelvin. It means 0 degree centigrade. And if pressure is 1 bar, alright, you have to remember this condition that STP means standard temperature and pressure, and where temperature is 273 Kelvin and pressure is 1 bar. You have to remember this. Alright, in the questions you will just be given STP. Okay, from there you have to deduce that if STP condition are given, that means pressure is 1 bar and temperature is 273 Kelvin. Okay, so at STP 1 mole, alright, 1 mole of any gas always occupies 22.7 liter of volume. Okay, so you don't have to remember this volume term. I'll tell you what you have to remember, but you have to remember that as long as I have fixed temperature and pressure, given moles of any gas will occupy same volume. Alright, if 1 mole of methane is taken, 1 mole of carbon dioxide is taken, 1 mole of sulfur dioxide is taken, 1 mole of nitrous oxide is taken, irrespective of which gas I am talking about, they will all occupy same volume. Okay, similarly like STP, there is another condition called NTP. Okay, NTP stands for normal temperature and pressure. Okay, here again temperature is 273 Kelvin, that is 0 degree centigrade, but pressure is 1 atmosphere. Alright, pressure is 1 atmosphere. Now there is a slight difference between bar and atmosphere. Okay, actually 1 bar is equal to 0.987 atm. Okay, 1 bar. You don't have to remember this right now. We'll study this in states of matter. Alright, and basically for your calculation parts, for your numericals in your exam, whether in your school exam or in your other competitive exams, we always approximate that 1 bar is approximately same as 1 atmosphere. Alright, see the difference, it is very slight. 1 bar is 0.987 atmosphere. So I assume that 1 bar is approximately same as 1 atm. Alright, so we always assume this 1 bar is approximately same as 1 atm, and once I assume that 1 bar is approximately same as 1 atm, I know that temperature is already 273 Kelvin in both the cases. So whether at STP or NTP, I can say that volume occupied by gases will be approximately same, and we assume that volume to be 22.4 liter. Alright, we assume that volume to be 22.4 liters. Okay, so you have to remember this. Okay, we don't take it to be 22.7 liter. We always take it to be 22.4 liter. It's just an assumption. Okay, you know that actually STP and NTP are different conditions. At STP pressure is 1 bar, whereas at NTP it is 1 atm. So the volume occupied by 1 mole of any gas will be different. Okay, so the volume occupied by 1 mole of any gas under both conditions will be different, and it is different slightly. Alright, here it is 22.4 liter and here it is 22.7 liter. But since 1 bar is approximately same as 1 atmosphere, okay, we can assume that STP and NTP conditions are kind of same, kind of equivalent. So we always take volume at under both the conditions to be 22.4 liter for 1 mole of gas. Alright, moles are fixed. You have to fix the moles in order to fix the volume. Okay, so for our calculations from now on, we'll consider this, but you have to remember the difference between STP and NTP. There is another standard condition that is called SATP. Okay, this is standard ambient temperature and pressure. Okay, this is standard ambient temperature and pressure. Ambient means the temperature that is in your surrounding, temperature and pressure which is usually present in your surroundings. Okay, so ambient temperature is taken to be 25 degrees centigrade, that is 298 Kelvin. Alright, again you have to remember this, that SATP stands for standard ambient temperature and pressure, and under SATP temperature is always 298 Kelvin. Okay, and pressure is 1 bar. Okay, pressure is like STP, it is again 1 bar at SATP. Okay, and here volume occupied by 1 mole of any gas, any ideal gas. Okay, here volume occupied by 1 mole of any ideal gas is 24.8 liter. Okay, now you don't have to remember this volume, and you cannot approximate it as 22.4 liter. It is much different from 22.4 liter. Alright, okay, so you have to make those calculations. We'll study how to make this volume calculations in states of matter. Okay, for now you just remember volumes at STP and NTP, and you have to remember the meaning of STP, NTP and SATP. Alright, there are other standard temperatures and pressures, okay, for used in civil aviations and aeronautics, but we don't have to go into them, and you neither have to remember them, but you have to remember these three. Okay, so now we know that once I fix temperature and pressure, okay, a given moles of any gas will occupy same volume. Okay. Let's do some mathematical analysis of this point. Okay, so now I know that 1 mole of any gas at STP or NTP is equivalent to 22.4 liter of volume. Okay, so 22.4 liter, that is, alright, 1 liter is 1000 ml, 1 liter is 1000 ml, so this implies 22.4 liter is nothing but 22400 ml. Alright, so 1 liter is 1000 ml, this implies 22.4 liter is 22400 ml. Okay, so 1 mole of any gas occupies 22,400 milliliter of volume at STP or NTP. You have to fix temperature and pressure first, okay, and then you have to fix the number of moles in order to calculate volume. Okay, so from this we can derive a formula. Alright, from this we can derive a formula using unitary method, basic simple unitary method. See, 1 mole of any gas at STP or NTP, okay, at STP or NTP occupies 22.4 liter of volume. So if I have, let's say, some random number of moles, say n moles of molecules, okay, again molecules, n moles of molecules, okay, so it will occupy, say, a volume equal to V liter, okay, a volume equal to V liter. So n mole occupy V liter volume and 1 mole occupy 22.4 liter volume. So I have to find a relation between V and n. What can I do? I can simply cross multiply. I can use unitary method. I can simply cross multiply. So what do I get? I get 22.4 multiplied with n is equal to 1 multiplied with V. So n is equal to, this implies n is equal to V divided by 22.4 liter. Okay, V divided by 22.4 liter. So I can calculate moles of a gas, okay, if I know the volume of that gas. Alright, so at STP or NTP, okay, you have to fix the condition. At STP or NTP, number of moles of gaseous molecules is equal to given volume divided by 22.4 liter. Why do I have to fix the condition as STP or NTP? Because this term 22.4 liter, this is at STP or NTP. If you change the condition, let's say from STP or NTP, I've changed the condition to SATP. Then instead of 22.4 liter, I will have to use 24.7 liter. Okay, what we saw in the previous slide. Okay, I'll have to approximately use 24 or 25 liter here. So in the denominator, instead of 22.4, what will come here? 24 or 25 liter. Okay, so in that case, number of moles of gaseous molecules will become equal to given volume divided by 25 liters. Okay, so that is why this formula is valid only at STP or NTP. If you change any one of them, let's say I fix the temperature as 273 Kelvin, but I change the pressure. Instead of 1 bar, I take it as 1.5 bar or 1.5 atmosphere. Okay, then again this term gets changed, 22.4 liter, this term gets changed, and I cannot use this formula directly. First I have to find what is the volume occupied by 1 mole, and then I substitute it here instead of 22.4 liter. Okay, so you have to remember all of this. Okay, you have to remember this formula. Okay, and once you do that, we can move on to examples for this law. Okay, so let's see the first example. First question says that you have to calculate volume occupied by 4 gram of hydrogen gas at STP. Okay, I have to calculate volume. I have been given mass. Now right now, until now, we have not studied any relation between volume and mass. What have I studied? I have studied a relation between moles and volume. I know that N is equal to V by 22.4 liter at STP, and condition that has been given in the question is STP. So I can say N is equal to V by 22.4. So I have to calculate V in the question. So I need N. N is moles of molecules, but I have been given mass. So next thing that you have to think about is how do I calculate moles. Alright, next thing that you have to think about is how do I calculate moles from mass. Okay, because you know that if you can calculate moles, you can calculate volume. So our task now becomes to find the relation between moles and mass. But we already know that relation. We know that moles of molecules is also equal to given mass divided by gram atomic mass or gram molecular mass. Since we are talking about moles of molecules here, not atoms, we use gram molecular mass. Okay, so N is equal to weight. 4 gram, given mass is 4 gram, divided by gram molar mass of hydrogen is 2 gram. Okay, hydrogen gas is H2. Okay, you have to know that. You have to remember this. Hydrogen gas is H2. So atomic mass of hydrogen is 1. So there are 2 atoms of hydrogen here. So 2 into 1 is 2 gram. So gram molar mass of hydrogen is 2. So 4 divided by 2 is 2. This means that I have 2 molecules of hydrogen gas. I have 2 molecules of hydrogen gas. Okay. So now I know moles. So I can directly substitute them here. I can substitute this value here. So I get 2 is equal to V divided by 22.4 liter. So V is equal to 2 into 22.4. Okay, 2 into 22.4 liter, which is 44.8 liter. So volume occupied by 4 gram of hydrogen gas at STP will be equal to 44.8 liter, and this is the answer for our question here. Okay, so give it a second to sink it in, and let's move on to next question. Okay. So in the next example, you have 2 moles of sulfur dioxide. First, what is sulfur dioxide? Molecular formula of sulfur dioxide is SO2. Alright, so you have 2 moles of sulfur dioxide. So So 2 moles of SO2 is pumped into a container containing these many molecules of the same gas. You have to calculate final volume of gaseous molecules assuming no change in temperature and pressure. Alright, actually this question will be incomplete. You have to assume here that the temperature and pressure maintained, okay, is at STP. Okay. Otherwise, if temperature and pressure is not given, we cannot calculate volume. So let's assume that temperature and pressure in the question is at STP. Alright, sometimes this happens. And the question, they have mentioned that assuming no change in temperature and pressure, but they have forgotten to return STP or NTP. So you assume that it must be at STP, because otherwise we won't be able to calculate the volume just by using moles. Okay, so either you write your answer as incomplete information because you clearly state that because temperature and pressure values are not given, or you assume that the temperature and pressure values are at STP and then you make your calculations. So assuming that temperature and pressure at STP and assuming that upon mixing of molecules there is no change in temperature and pressure, we can make further calculations. So I have a container. What I'm going to do, I'm going to pump 2 moles of SO2. I'm going to pump 2 moles of SO2 inside this container. Okay, I have already some molecules of SO2 present in this. Okay, there are some molecules of SO2 already present in this container, and that number is N is equal to 3.011 multiplied with 10 to the power 23. Okay, so I have these many molecules. Here I have moles. Okay, let's convert all of them into same figure. Okay, these are number of molecules. Okay, not moles. So let's convert them into moles. If you remember, number of moles of any particles is equal to number of particles divided by Avogadro's number. Okay, if you remember this from a previous session, that number of moles is equal to number of particles divided by Avogadro's number, Na. Okay, so that is number of moles already present inside the container is this divided by 6.022 into 10 to the power 23. So this comes out to be 1 by 2 or 0.5 mole. Okay, so I have 0.5 mole of SO2 gas already present in the container. Now in the same container, I am purposefully adding 2 moles further of SO2. Okay, since I have increased the number of moles, initially I had 0.5 moles of SO2. Okay, it doesn't matter which gas is present. Okay, though you have been given SO2 in both the cases, we know now that it doesn't matter which gas is given, because Avogadro's law is applicable irrespective of the type of gas. So it doesn't matter whether it is SO2, N2O, CO2 or any other gas. Okay, so 0.5 mole of SO2 or 0.5 mole of a gas, okay, we always assume them to be ideal gas. So 0.5 mole of a gas is mixed with 2 moles of another gas. So I have now 2.5 mole of gas. I have 2.5 mole of gaseous molecules in my container. Okay, so to maintain temperature and pressure, what will happen? Moles have increased from 0.5 to 2.5. Okay, from 0.5 moles have increased to 2.5. It means volume will have to increase. Okay, at same temperature and pressure. Okay, if I am assuming that there is no change in temperature and pressure, increase in moles will result in increase in volume. Alright, so now I have to calculate what is that volume. Okay, after increase of moles, what is the volume? Let's see. I know that N is equal to V by 22.4. I know that N is equal to V by 22.4. So V is equal to 22.4 into N, where N is moles of molecules. So moles of molecule is now 2.5. So answer will be 22.4 into 2.5. Alright, answer will be 22.4 liter into 2.5 moles liter per mole. So that means I have 2.5 into 22.4 liter of gas inside the container. That is 56 liter of gas is present at STP inside this container. Okay, this will mean that the volume of container was not fixed in this case, because I have increased moles at same temperature and pressure, so volume has to increase. There is no other option, otherwise you won't be able to pump in the 2 mole of gas, it won't go in. Okay, so hence volume has to increase, and volume increased from some initial value to 56 liter. Okay, let's see another last example on Avogadro's law. Okay, in this example you have 3 mole of ozone gas which occupies 44.8 liter volume at certain temperature and pressure. What volume shall be occupied by 1 mole of nitrogen at same temperature and pressure? See, at STP, if the condition of temperature and pressure was STP, I know that 1 mole at STP occupies 22.4 liter. It means 3 moles at STP will occupy 3 times the volume, that is 3 into 22.4, okay, which gives me 67.2 liter of volume. Okay, you can use the formula N is equal to V divided by 22.4, or you can directly say that 1 mole occupies this much volume, so 3 mole will occupy 3 times that volume. So 3 times 22.4 is 67.2 liter. Okay, but here I have been given that 3 mole of ozone gas, any gas. Okay, we don't care about the name here. So 3 mole of any gas. Okay, let's not get confused by the name of the gas. 3 mole of any gas occupies 44.8 liter. It means the condition of temperature and pressure is not at STP. Alright, it is not at STP. So you cannot use that formula N is equal to V by 22.4 liter here. Okay, in this question you cannot use that formula because the temperature and pressure condition have not been given to be STP or NTP. Okay, so what do we do? Let's see the question again. We have 3 mole of ozone gas. Okay, I have 3 mole of ozone gas which occupies 44.8 liter volume. I have to calculate volume that will be occupied 1 mole of nitrogen. Now see, we all know that irrespective of temperature and pressure, the type of gas has no effect here. So whether it is ozone, whether it is nitrogen, it doesn't matter as long as it is a gas. So now the question becomes that 3 mole of ideal gas occupies 44.8 liter. Then how much volume will be occupied by 1 mole of gas? This is what question actually asked us to calculate. That if 3 mole occupies this much volume, how much volume will be occupied by 1 mole? So what do? I simply use the unitary method, go to basics. Whenever in doubt, go to basics. Alright, forget about formula, go to the most basic thing that you know is unitary method. So 3 into V is equal to 44.8 liter. So V is equal to 44.8 divided by 3 liter. Alright, so volume occupied by 1 mole of any gas at that temperature and pressure. The temperature and pressure given in the question, we don't have to know that because we have already been given relation between moles and volume here. So we didn't actually need to know the value of temperature and pressure. We just need to know that it is maintained to be constant. So at that temperature and pressure, volume occupied by 1 mole of any gas. So 1 mole of nitrogen gas will also occupy 44.8 by 3 liter of volume. Okay, so this finishes up our concept of Avogadro law. Alright, so try and get some more practice of this topic. Alright, solve some more questions. It's very important topic. You don't directly get questions on them. Alright, you might get a 2-marker question, okay, or 1-marker question, but usually it is used in your more complex questions. In fact, all of the topics that we'll study in mole concept, we very rarely get direct questions from them in your competitive examinations. okay, or even in your board or school examination you might get 1 or 2 questions max. Okay, but these topics, all of the mole concepts, all the sections in the mole concept are sub parts of your questions. Okay, they'll form the subsections, okay, which we'll use for furthering our study of physical chemistry into different topics. Alright, so until next time, and once again thanks for watching Edupedia World videos.